Welcome to the first video tutorial of the series for CPP Robotics' Zoombot project, a project all about learning Arduino microcontrollers, various circuit elements, and sensors. Our tutorial videos will take you from introductory wiring and circuit concepts all the way to Arduino programming and usage. The first few videos are going to be all about electrical circuits. In this video specifically, we're going to talk about voltage, current, and resistance. We're going to see how they're all correlated with Ohm's law, and then we'll wrap up the video with a discussion on power. Let's delve into the three main electrical concepts: voltage, current, and resistance. First, I'm going to describe these to you with their electrical definition. Then, to make it make a little more sense, I'm going to describe electricity as water flowing through a system of pipes. Electricity can be hard to understand since you usually can't see it, so thinking of it like water is going to help with you understanding its characteristics. So let's go ahead and start with voltage. Voltage is the potential difference between two parts of a circuit. Voltage is measured in volts. And the easiest example of voltage is in something like a battery between the two ends. 1.5 volts means there's a potential difference of 1.5 between the two ends of the battery. Relating this to water, think of the voltage as how high a bucket of water is in reference to the floor. You can also look at it like the water pressure inside of a pipe. The higher the bucket of water is, the harder the water will fall to the floor. The higher the water pressure is, the easier it is to force water through a pipe. So the higher the voltage is, the stronger the electricity is sent through a part of the circuit. The second concept is current, or the flow of electrons through a part of a circuit. Current is measured in amps. And while I don't have a direct example of something like raw electricity, a relatable example is going to be through your phone charger and how many amps it says that it can output on the back. 1 amp means that there's 1 amp's worth of electrons flowing through a section at a specific point in time. Relating this to water, think of current like the actual water that's flowing through the pipe. The more water there is flowing through the pipe, the more water there is to use in your system. If you're trying to spin a water wheel, that's going to require a certain amount of water to actually get it spinning. Trying to power an LED, you'll need a certain amount of current flow through the LED to actually get it to light up. The third concept is resistance, which is a force that works against the flow of electricity. This force is measured in ohms. The easiest example I have for you is with a resistor itself. These are crucial to most circuits, and we're going to be using them throughout the Zoombot project. 500 ohms means that there's 500 units of resistance pushing back against the flow of electrons, the flow of the current. Think of resistance like a valve in a water pipe that restricts the flow of water. The tighter the valve is closed, the less water that will be able to flow through that pipe. The higher the resistance, the less current, the less electrons that can flow through the resistor. Now that we understand voltage, current, and resistance, let's explore how the three are related. You can combine these three into an equation and then use that to find parameters of a circuit element. This equation is called Ohm's law, and it goes like this. Voltage is equal to the current times the resistance. Usually you're going to see it as V is equal to IR. This is really useful because you can find one of those elements when you know the other two. For example, if you wanted to know the amps traveling through a certain part, you can reorient it into I is equal to V divided by R. If you wanted to know how many ohms you might need for a resistor or a certain part, you can orient it into R is equal to V divided by I. The best way to learn how to use Ohm's law will be through an example. So we have a 500 ohm resistor, and we're going to have a 5 volt power source. We can ask how many amps are going to flow through this resistor with that criteria. What we do is we start with Ohm's law. V is equal to IR. Reorient Ohm's law into I is equal to V divided by R with some algebra. Now we plug in what we know. Plug in the 5 volts, 500 ohms, just like that. And you end up getting that your current is going to be 0.01 amps or 10 milliamps. You can use this process to ask the question of how much water will be flowing through a pipe with this much water pressure and this valve. So with this resistor and this voltage, how much current is going to flow through it? Doing another example, let's say we have 5-volt source again, but we want 70 milliamps running through our resistor. What is the value of that resistor? So let's start with Ohm's law again. Let's reorient this for resistance. So it's going to be resistance is the voltage divided by the current. Let's plug in what we know. And then we get the resistance to be around 71 ohms. Like that. With a process like this, you can ask the question of how strong of a valve will I need to limit the water flow to 70 when the pressure is 5? So what resistance value do I need to restrict the current flowing through it when the voltage is 5 and I want the current to be 70? Knowing the correct resistance you need for a circuit element is critical, but resistors don't come printed with the values directly on them. Instead, they have a color and band scheme of 4 or 5 bands printed. Now the color and their respective position is going to have a different meaning, so it's important that we know exactly how to read that. Now the resistors in our kits are going to have 5 bands, and that's what we're going to be talking about for this video. But know that there's also the 4-band scheme, which is what we're used to in ECE, but just know that they're going to have the same end result. The first 3 bands represent your resistance values before a multiplier is applied. The first band is the hundreds place of the number, the second band is the tens place, and the third band is the ones place. To represent different numbers in each band, we also have different colors. Starting from black and ending with white, the digits go from 0 to 9 accordingly. Check the screen for which colors represent each digit. If you wanted a resistance value of 560, you would choose a resistor with the first band as green for 5, second band as blue for 6, and the third band as black for 0. If you combine these numbers into 560, you get 560 ohms. The fourth band is the multiplier band, and it will multiply the value of the first 3 bands by a specific amount. The multiplier starts at 1 for black and gets 10 times bigger with each color shift. Check the screen again for which color represents the multiplication value you want. Additionally, we have 2 new colors, gold and silver. A gold band means a 0.1 times multiplier, and a silver band means a 0.01 times multiplier. For 560 ohms again, we already have the 3 bands that give us the desired resistance. Therefore, we choose a resistor with the multiplier band as black, so that just multiplies the value by 1. If we wanted 5600 ohms, for example, then we choose a resistor with the multiplier band as brown. 560 times 10 equals 5600. The fifth and final band is the tolerance band. It basically tells you how good of a resistor you have. The lower the tolerance, the more accurate of a resistance your resistor will provide. Tolerance value means it could be a certain percentage higher or lower than the printed resistance value. Once again, check the screen for how the colors relate to their tolerances. A resistor value with a silver band as the fifth band, or 10% tolerance, means that for a 560 ohm resistor, you can actually see values between 504 to 616 ohms. Tolerance shouldn't be an issue with our Zoombot project, but just know that high tolerances can ruin circuits that do require precision. The final concept we should discuss briefly is power. In the case of circuits, you can think of power as the heat generated from your circuit while it's running. A direct example of this is going to be what you feel from your computers. All that heat being generated is electricity running through circuits. Now, our project should be generating nowhere near as much heat, but it's still important to consider with something like a lot of LEDs in our circuit. Now, you can determine how much power is generated based off of the following equations. Power in a specific part is equal to the voltage across that part times the current going through that part. The other equation is power is equal to the current squared times the resistance. Let's do another example to see exactly how power works. So if we have 5 volts going across a 560 ohm resistor, In order to find the power going through that resistor, first we need to find the current. So let's go ahead and use Ohm's law, which is V is equal to I times R. It's reoriented for current. I is equal to V over R. Plug in what we know. 5 volts, 560 ohms. And we end up getting 9 milliamps. Now that we have the current, let's go ahead and use the power equation. We'll do this one with volts times current, P is equal to V times I. Let's plug in what we know. So we know that it was 5 volts times now the 9 milliamps, or 0.009 amps. And our power ends up being, extra 0 in there, or we end up having our power is equal to 45 milliwatts. The resistor here is going to be burning this much heat, resisting that current flow trying to go through the resistor. So you could say this valve is heating up, making this much heat, trying to resist the flow of water that's going through it. Considering power is important because you can burn some circuit elements if they're generating too much power. For example, the resistors in our kit have a rated max power of 0.25 watts or 250 milliwatts. You can think of this as the max heat they can take before possibly breaking. So to be safe, try to keep the power generated in a resistor below 3/4 of its max power. That concludes our look into some introductory circuit concepts we'll need for the Zoombot project. In the next video, we're going to put those to use and actually create some circuits and see how they work. If you have any questions about the material we covered here, make sure to reach out to us on Slack. You can reach out to me, Gabriel Contreras, you can reach out to the officers, or any of the other project leads or members involved with Zoombot.